Okay. Hello everyone. Today I'm going to talk about a research paper called Optimizing for Recall in Automatic Requirements Classification, an empirical study, and share my study process with you all. Nowadays it is not an ideal solution to use machine learning in requirements engineering problems for the recall because the recall is usually under 100% even with a powerful algorithm. So when we use machine learning skills, we need to seriously consider the balance between recall and precise. However, sometimes there are some complicated problems in which even requirements engineers can solve them perfectly, so it is necessary to find a tool whose performance is comparable to a trained engineer to save their time and resources in solving this kind of problems. Okay, then I would like to introduce some background information for you. First is about requirements specification. It contains the properties that a system needs to exhibit and derivation of test specifications and defines liability between stakeholders. Besides, specifications also contain non-requirements, which includes examples and explanations. It is significant for understanding requirements and their context. What's more, explicit differentiation between requirements and non-requirements can improve the quality of the requirement specification and the correct answer, create the correct software that stakeholders want exactly. Second is automatic requirements classification tools. Classification tools represent a convenient solution to support a requirements engineer in classifying requirements and can be used to distinguish functional and non-functional requirements. Third is automatic classification of requirements and non-requirements. The approach is based on convolutional neural networks and also offers a visualization component to help engineers understand the decision of the classifier. We also conducted an experiment to determine the usefulness for our tool. From the results, we know that an optical balance between precision and recall is crucial for a tool that aims to assist a requirements engineer. Fourth is calculating f-beta. F-beta to evaluate and optimize classification tools. Here are some basic concepts which can evaluate the assistance tools. Precision indicates the percentage of correct answers over all answers found by the tool. Recall indicates the percentage of correct answers found by tool over all possible correct answers. The composition of both evaluation metrics is called F-measure, and for the best one, summarization indicates by how much an original document is reduced. Besides, we use F-beta to evaluate tool assistance. In this paper, the author analyzed the classification of specific content elements into requirements and non-requirements and assessed the importance of recall by empirical study. In this study, the authors compared two groups of students with and without tool support. Later on, we can choose the optimal balance between recall and precision and access the practical savings through the results. Finally, we can prove the practical usefulness of our machine learning tools. Next, I want to talk about the summary of evaluation results. From the results, we can derive two main conclusions. First, finding defects with the help of a classification tool works better than working on the original data. Second, using f-beta instead of f1 for optimizing the tool makes sense and reduces the number of elements that need to be examined by a human by 61%. Okay, in this part I'm going to talk about the research design and methodology. In this empirical study, we compare two groups with and without the tool to measure improvements by the tool. As we can see from the experiment design table, control group means the task is performed manually, that is, without any support by the tool. Treatment group means that it inspects only the elements containing defects as determined by the automatic classification tool. And then we have three major topics in this research, which are the performance difference between two groups, the optimal beta for the requirements, non-requirements classification task, and how big is summarization given beta on typical requirement specification documents. Then we choose the specification of the two systems, which are wipe control system and the hands-free access system, and their functionality is easy to understand. We can see the statistics about the final documents from Table 2. Next, I want to talk about the evaluation plan. First is performance difference between the groups. We will compare both groups with the following matrix. The defect detection recall measures how many defects a participant finds in the specification. The defect detection precision measures how many changes of a participant actually fixed a defect. The time per element measures how many seconds a participant spend on average to make a decision for one element in the specification, and the total time per review should still be greatly reduced and due to the significantly smaller number of elements in the review. Second is calculation of beta. We calculate beta as described below. For this formula, first part is the average time of a participant in the control group to identify and correct a defect. Second part is the average time of a participant in the treatment group needs to either accept or reject a single answer from the tool. Second is calculation of F beta and summarization. We will estimate average summarization of the tool by using beta and a synthetic test. Finally, I would like to introduce the study results. From figure 1, 2, 3, and 4, we can conclude that by using the tool in reviews increases precision and recall on defect detection and decreases total time needed by the participants significantly. For the calculation of beta and summarization, we can calculate the beta for our classification and get the result of 6.18. Besides, from figure 5, we can conclude that we cannot achieve both high precision and high recall. Then we use precision and recall to calculate both F1 and F beta with beta set to 6.18. The results are displayed in figure 6. From this figure, we know that we should optimize the classifier by setting the error detection threshold to 0.15, and these values represent a good balance between recall and precision for the classification task. However, there are still some limitations in this research. For instance, students may don't have sufficient knowledge and experience in such tasks compared to experts, so the results may differentiate with each other and influence the beta. So that's all the discussion. Thanks for watching.